Hi, this is a short demonstration of our toolchain to develop smart contracts on Bitcoin. The toolchain is based on BitML, a domain-specific language for contracts which compiles to standard Bitcoin transactions. We use BitML to develop a lottery, where two players bet 1 Bitcoin each, and the winner, chosen uniformly at random, gets 2 Bitcoins. To determine the winner, each player secretly flips a coin. If the two sides are equal, the winner is the first player, otherwise it is the second player. We develop this contract within the Dr. Racket environment. First, we declare the two players, Alice and Bob, and we associate them to their public keys. The contract requires some preconditions before it can be stipulated. The preconditions tagged by deposit require players to provide their bets. Each bet is represented by a transaction with 1 Bitcoin, which must be redeemable with the private key of the participant. Once the contract is stipulated, these 2 Bitcoins are no longer available to the players, but are controlled by the contract. The other preconditions require each player to commit to a secret, which models the flipped coin. In the precondition, the players only declare the hash of the secret, not the secret itself. The hash is used during the contract execution. When the player claims that she is revealing the secret, the hash of this secret must coincide with the hash in the precondition. The contract is a choice between 2 branches. The first branch is enabled if both players reveal their secrets, and the secrets are equal. In this case, the contract transfers to Alice the 2 Bitcoins deposited in the contract. Otherwise, if the secrets are different, then only Bob can withdraw the 2 Bitcoins. By clicking the Run button, we obtain a set of transactions, expressed in the Balzac abstract language. Balzac is one of the components of our toolchain. It translates these abstract transactions to standard Bitcoin transactions. Executing the BitML contract corresponds to appending these transactions to the blockchain. Our toolchain can also verify security properties of contracts. For instance, we want to check that the lottery contract is liquid. This means that funds do not remain frozen forever within the contract. We verify this property by playing the role of Alice, assuming that her strategy is to reveal the secret. We do not specify Bob's strategy, because we are assuming that he is the adversary. The verifier says that the contract is not liquid. This happens because if Bob refuses to reveal his secret, he blocks both branches of the choice. To cope with this issue, we must modify the contract, to incentivize Bob to reveal. To this purpose, we ask Bob to deposit a collateral of 2 Bitcoins, and pay it to Alice if he does not reveal before a certain deadline. We do the same on Alice's side. To do this, we split the balance in 3 subcontracts. In the first one, if Bob does not reveal before block 1000 is added to the blockchain, then Alice can get 2 Bitcoins. The second subcontract is similar, inverting the roles. To achieve fairness, we require secrets to be 0 or 1. The third subcontract pays 2 Bitcoins to the winner. Now we verify that if Alice reveals, eventually she will have at least 2 Bitcoins. More precisely, we assume that Alice chooses the secret 1, while Bob can choose either 0, 1 or 2. The verifier says that the property holds. However, the contract is still not liquid. From the counterexample, we see 2 Bitcoins may remain frozen in the third subcontract if Alice or Bob do not reveal. In this case, after block 700,000 we return 1 Bitcoin to Alice and 1 Bitcoin to Bob. Finally, the contract satisfies our properties and is liquid.